Hello, welcome everyone. We're excited to have you here with us today on our webinar, The Importance of Managing Pressure Drop and Thermal Solutions. Thank you for joining us. My name's Mac Brown. I'm the Business Development Manager for North America here at Conflux Technology, and I'll be your host for this session. So today's topic is it's one that's most critical, right? But often overlooked aspects of thermal management. Pressure drop, whether you're working in aerospace or motorsports or industrial applications, understanding how to manage pressure drop is essential to optimizing both performance and efficiency, and something we focus on highly here at Conflux. Before we get started, just a few housekeeping notes. This session is being recorded, and we will share the recording and key resources with you afterwards. If you have any questions during the presentation, you'll see the Q&A box there. We'll have a dedicated Q&A section at the end of the address and try to answer as many questions as possible. So here's what you can expect over the next 45 minutes. We'll start with a deep dive into the science and impact of pressure drop in thermal systems. Then our engineering team will walk you through Conflux's approach to simulation, profiling, and real-world validation. And then finally, like I said, we'll wrap it up with a Q&A. I am joined today by Isaac, one of our solutions engineers. Quick note, Ethan is unable to join us today, so Isaac will be presenting the webinar, and our lead solution engineer, Brian, will then be joining for the Q&A session. So with that, let's get into it. Isaac, I'm going to pass it over to you.
Thanks very much, Mac. Hello, everybody. Thanks for joining. I'm Isaac Su, Solutions Engineer at Conflux Technology. And like Mac mentioned, today we'll dive into pressure drop, what it is, why it matters, and how we design around it. So just starting with the definition, what is pressure drop? It's simply just the loss of pressure that a fluid experiences as it moves through a system. And this can be due to changes in velocity, direction, and fluid properties as well. We can just think of it as overall the mechanical load that our heat exchangers put on a system. And we measure the pressure drop from the inlet to the outlet, usually of either fluid stream. Main causes, mostly due to wall friction, especially in the high performance core or the central region of our device. But the manifolds also can expand and contract the fluid and turn and route the fluid as well. This can contribute to pressure drop as well. Fluid changes, changes to state, especially due to the thermal transfer within the device, can also lead to pressure drop in our heat exchangers. But the question is, why does this really matter? In most of our designs, the core is the majority of the pressure drop, with the manifolds also contributing. It matters the most because the pressure drop fundamentally drives the heat exchanger design, the size, the type, and the layout. And so the pressure drop constraints we work within when designing our heat exchangers are really, really important. Now, we're always trying to maximize heat transfer in our devices, but balancing the heat transfer rate against the pressure drop resistance of the system can be a challenge. So why does it matter? It matters because our heat exchanger doesn't exist in isolation. It's actually embedded within a larger system. So here, for instance, is a water to air heat exchanger to cool down water in order to then reject heat out of, say, an electronics cooling system. Now we need to consider all of the components, the pumps, the fans, many other aspects of the system, as well as the heat exchanger itself. And this is in order to promote system harmony. So if we're able to manage and minimize the pressure drop in our device, we can improve the overall system efficiency. And this, over time, a small reduction in pressure drop can lead to really great efficiency and cost savings depending on application. We don't just want to minimize the pressure drop. We actually need to factor in the sweet spot operating range for the pump curves, the fan curves, and how our heat exchangers pressure drop profile interacts with these two as well. This is all really important to promote overall stability and long-term operation. Now, if we can minimize the pressure drop or quite accurately manage the pressure drop in our heat exchanger, then we might be able to right size, say downsize a pump or a fan, and create greater system level efficiencies and weight savings as well. But as I'm going to get to next, there's actually quite a trade-off that fundamentally underpins pressure drop in heat exchangers. And this relates to the fundamental heat exchanger equation, right? Your Q equals U times A times delta T. And this gives us three basic levers that we can use to increase the heat exchange in our devices. We're always trying to drive to maximum heat exchange, but this is in tension with pressure drop. So we can increase the temperature difference of the two fluids. This isn't practical. We often don't have the ability to change the inlet temperatures. This is applied by the system itself. We do have some control over the U, the heat transfer coefficient, where we can promote turbulence and disrupt the flow within our heat exchanger itself. But you often find yourself limited or bound up by the fluid properties themselves. So no matter how much you increase the interaction with the wall, the inherent conductivity, etc., of the fluids can still limit the U value. So we get the most bang for our buck by being able to pull the lever of surface area. And that way we're able to cram as much geometry as possible into a small volume and maximize heat exchange to volume ratio. It's worth noting that the surface area sits as the linchpin in between heat exchange and pressure drop, and varying surface area has a dual impact on both. You can't maximize the heat exchange and minimize the pressure drop together, at the same time as easily. There's actually a balance required because these two objectives work in tension with one another. So there are a lot of pros to being able to minimize the pressure drop in our heat exchangers, like we've just mentioned: system harmony, efficiency, being able to reduce the weight and size of other components in the system. But there's some key cons as well. As we would drive down the pressure drop in our heat exchangers, we might fundamentally need to reduce the amount of surface area or the amount of obstruction that the fluid undergoes. So this can reduce the overall heat rejection of the device. If we want to combat that and counteract that effect, we might need to resize the device, say a larger device frontal area. We might need to shorten the flow paths, or we might need to do a combination of that with core density as well. And this really speaks to the non-linear relationship of heat exchange and pressure drop as well. And we'll get to that further into the analysis, but you get plateauing or diminishing returns by adding increased surface area into the device. And at the same time, so diminishing heat exchange returns, but at the same time, the pressure drop really starts to exponentially increase. So the question is, how do we best approach this trade-off, and how do we maximize heat exchange and minimize pressure drop at the same time? Now, this is where additive manufacturing gives us a few key advantages. So the actual technology itself is really, really useful for us to be able to put as much surface area as possible into quite small volumes. Looking into the core now, zooming into that, we're able to then we're able to quite well manage the flow as it enters the core, and this is through high levels of flow control, especially through the manifold region of the device. And once the fluid enters the core itself, then we're able to use the advantages of additive manufacturing, the flexibility it provides, really. We're able to then vary the core density throughout the device itself. So as a fluid might change state or properties, as it absorbs or rejects heat, we can match the core along its flow path to really squeeze out as much heat exchange as possible before it leaves the device. Now, the surface roughness effect of additive manufacturing actually creates some advantages and some drawbacks as well, because at quite a small scale, the roughness of the surface can improve the heat transfer coefficient U, but it can also increase the pressure drop of the fluid passing through the device by reducing the effective hydraulic diameter, that the amount of space that the fluid has to pass through. So it can unduly increase the resistance that way. You know, one final advantage I'll just mention about AM is you can see on this image, it's a monolithic component. So we've integrated the core into the manifold, into the ports and fittings seamlessly. This can reduce overall number of components that we need to produce. It can minimize the complexity, and most importantly, it actually reduces the number of points of failure in between these components by printing it monolithically. Now, how do we use additive manufacturing and how do we get the most out of it? How do we leverage it for the best result? Now, we've got our business sits in the Venn diagram of design, additive manufacturing, and simulation teams. So we've got 3 different departments that all work in conjunction to push the envelope and really drive our heat exchangers to the next level. The design team, they have extensive experience tailoring heat exchangers on a need-by-need and a case-by-case basis. They're able to create high-quality, bespoke solutions that really match the customer needs. Now, over time, this is aggregated into quite a large library of configurable heat exchangers, which we can then apply into different situations we face ourselves. Now, I'm a part of the simulations team, and design and simulations do go hand in hand. So it's an iterative loop that we often undergo between the design, the testing, the simulation of our components, and then we compare them against experimental results. So to do so, we use the first principles design approach to get convergence on the best possible solution to the problem. We do this with a bit of CFD and FEA, and all of this is to say that the simulation team and the design team worked really well and really pushed the envelope, but we're fundamentally limited by the additive manufacturing process. So it really matters what we're able to stably print and stably build in the workshop. And this speaks to the importance of process and parameter development in the workshop team. So all of this matters is because all 3 of these departments work hand in hand, and we need to consider what the progress across all 3 divisions in order to then make the most stable and high quality heat exchangers. Now, I mentioned I was part of the simulations team, so I'll be able to discuss a bit more of the analysis side of things here today. And that's what I'm going to do right now. When we analyze the heat exchangers that we design, we break them up into the components and we analyze them on a piece-by-piece basis, and we consider them individually and collectively as a whole. So the device you can see on the screen here is a counterflow orientation, which means the fluids flow against each other, and this maximizes performance. Most of the pressure contribution comes from the core region of our device, and this is where you get really high fluid interaction with the walls, the most blocked flow path, I suppose. And this really contributes the most to our pressure drop in our devices. It's worth noting that as the fluid enters, it enters through a manifold. It might need to turn, it might need to expand or contract. All of these, and including the interaction between the manifold and the core, these 5 components tend to add the most pressure drop to our device. Now, when we actually consider how we analyze these devices, we need to break it down and consider from multiple levels of analysis. The whole model itself gives you a great overall picture of how the fluid enters, passes through the heat exchange, through the manifolds, the interaction with the core. But then we're able to actually start stripping back the different elements. So we might remove the air manifold or the gas manifold in this instance, just consider the core with the liquids. Then we might zoom in closer in order to sort of analyze, say, hotspots or flow distribution on a certain critical section of the device before we zoom right in to the subcore level. And this is what gives us the most high fidelity, high resolution simulations that really are able to capture that fluid wall boundary layer and how we can optimize and maximize performance at a minimal scale. So we need to consider all of these levels of analysis and the benefits they bring in order to analyze our whole device and to get really accurate readings on the pressure drop of it. Because the core contributes the most to the overall pressure drop, I'll double click on that next, and we'll look at how we actually analyze the pressure drop within the core itself. So we've done a lot of analysis, we've done a lot of simulation design, we've created lots of libraries of data. But here's the thing, the traditional heat exchanger equations for predicting pressure drop and heat transfer don't apply to our complex, sophisticated heat exchanger designs. So we have to combine our experimental testing with those high fidelity simulations to build our own data sets that we then use to correlate against and make accurate performance predictions of how parts will perform before we even press print. How we use pressure drop and how it relates to heat exchange inside the core itself is really interesting. So I'll just talk quickly about a sizing example, and this is a position we often find ourselves in. Over to the right, you can see a plot, and this relates surface area, heat exchange in green to pressure drop in purple. And as we start to increase the amount of surface area in the core by building up the density, putting a lot more walls and surfaces in there, you can see what it does to both heat exchange and pressure drop, right? It has diminishing returns on the heat exchange. So more and more surface area gains start to really plateau out as you approach the physical heat exchange limit. And there's an inverse relationship with pressure drop as well. So you exponentially start stepping towards, I suppose, infinity, and then the device becomes blocked and then no fluid can pass through, which leads to no heat exchange anyway. So we end up being able to draw a solution space or a bounding box around appropriate density, heat exchange, and pressure drop results. And so for a given system, you might be limited on the pressure drop and you might have a heat exchange target, but how you can meet both of these at the same time is really where the challenge is. This matters so much because as the pressure drop limit changes or how these two interact, it can limit or change where that solution space sits and the size of the available window that you have to be able to put optimized geometry into a solution that meets all the targets. So all of this is to say that it can be a challenge. The world wants more and more from heat exchangers. So managing pressure drop in the device really requires a lot of empathy for the system. We have to work quite closely with our clients to understand their system level constraints and what we can use for a bit of give and take, how we optimize our device across the pump curves, the fan curves, the available space, the thermal targets, overall objective, thinking outside the box. These are all some ways that we help to alleviate the gridlock and challenge from managing the pressure drop. Now, I might move into a few industry challenges and trade-offs now before we have a quick look at a few case studies. Within automotive and motorsport, I'll start there. This is where Conflux made its emergence. This is where we began. And in this industry, performance, packaging, and weight, they're king. They're so important to minimize and maximize as well. Now, vehicles are increasingly demanding more compact, powerful engines, which means the most heat exchange possible, and they need minimum pressure drop as well. But, in this industry, space constraints are often super duper tight. So we might encounter short flow paths, sharp turns, complex manifolds. All of these aspects can increase the pressure drop. Now, back to a few of those key advantages, they really apply into automotive and motorsport. Now, we find great gains from being able to embed our complex heat transfer surfaces into conformal spaces to occupy as much area as possible. We also need to manage the flow really, really well in this industry. And in order to reduce weight, we might be able to integrate multiple components together. And this really can help simplify and minimize the overall weight on the vehicle. So these few advantages are really how we're able to exploit additive manufacturing to give the best heat exchange to pressure drop ratio possible in automotive and motorsport industry. Next, I'm going to talk about aviation, and I'll get through the rest of them as well. In aviation, the goals are quite similar to motorsport. You've got ultra lightweight, high performance, and extremely low pressure drop targets. We find a really great advantage by being able to shape our devices to actually meld quite well with the available space of the airframe. And this can really help us minimize the parasitic drag that our heat exchangers might apply in, say, a ram air cooler. But all of that said, our parts need to become airworthy. And qualifying parts up through the TRL levels is a really good challenge for us at Conflux. It helps us push our capabilities, but at the same time, those tests are really strenuous. We might be encountering salt, vibration, inertia, explosive atmosphere tests, all of that, just to name a few. Like aviation, when we consider the space industry, we also need to design for long operational life and a really high reliability part. And so cooling systems on the aircraft, they often use really low power pumps or fans. They might not have the most not have the most weight availability, so the pumping power can be quite limited. So we need to find a way to put our heat exchangers into this system, and how do we minimize the pressure drop in order to promote that overall system harmony? It's really tough in space, and our heat exchangers might be exposed to some of the toughest conditions out there, cryogenic propellants, high pressures, liquids, intense thermal cycling. And this is all captured by NASA Standard 6030, which outlines the requirements for our heat exchangers. We need to reliably make really strong, leak-free, high-performance parts in incredibly constrained volumes, all while tolerating those tough conditions. So it's really important to not only maximize performance, but also maximize durability wherever possible. I'll move now to defense, where, like space, the military systems can operate in really harsh and unpredictable environments as well. Large shocks, large vibrations, and G-forces are all some things we expect. Similar to space, the cooling power and the amount of available fan or pump or battery power that we might have at hand might be limited. Alongside this challenge, the fouling and environmental pollutants like dust, sand, salt, and frost can all be things that the heat exchanger, if exposed to the environment, might be blocked by, throttled by, and this will effectively drive up the pressure drop in that device. So again, similar to space, in defense, we really need to push extra hard on the durability side of things and the reliability side of things as well. I'll finish by talking about industrial, which is quite a good transition, because reliability and stable operation really matter, along with the durability and serviceability too. In industrial systems, from data centers to chemical plants, they will prioritize uptime, reliability, and energy savings. So here, being able to minimize pressure drop can lead to great operational advantages, especially over thousands of hours. Little gains can really, really add up. So we need to design a part that's not only high performance and low pressure drop. We might also experience really tough fluids, and so fouling and the fouling build-up over 24/7 operation can be a factor. Now, we might oversize our parts or upsize our parts to really help promote serviceability, cleanability, and account for that fouling factor as well. I'm going to move now into some case studies across a few of the sectors that we serve before we can jump into the Q&A section. So our first case study is really interesting. Xtrac is a high-performance transmission manufacturer, and they engaged us to develop a solution to cool down super hot gearbox fluid in order to keep the engine in a stable range while it is pushing the limits and driving it at maximum conditions possible. We needed to retrofit our heat exchangers into an existing housing. So we needed to really accurately conform to the available space and put as much heat transfer surface into the existing housing available. In order to do that, the approach we took was we reconfigured one of our configurable rectangular cartridges into the annular or circular cartridge you can see up on the screen. And this really helped us to meet the housing demands. And when we were doing the design of the cartridge, a lot of effort was put into optimizing the pressure drop of the heat exchanger, especially across the whole engine range, the amount of RPM of the engine, and all of the flow rates that our fluids would expect to endure. So we needed to maximize the performance and minimize the pressure drop. Great advantage was being able to really well distribute the flow. And at the same time, this had to trade off against the durability of our device. Why? Is because it eventually went on to be road and track certified. So now, after extensive, really tough tests, our part is certified for track and road. It led by being able to put so much surface area into the space and being able to optimize and really to min-max the heat exchange and pressure drop. We're able to actually squeeze out an extra 30% heat exchange over the incumbent, which enabled that gearbox to cool down, gearbox oil to cool just enough that the solution was a great success. Again, it gave us total conformability to the envelope, and it's a plug-and-play replacement that just slots right in. A similar industry, a similar space to that is the high-performance automotive and motorsport. Now, what we did here was we were engaged by a company called Donkavort to design and develop a water-charged air cooler, which would help cool down the quite hot air as it leaves the turbocharger and before it enters the engine. In this instance, it was really important to have the outlet as cold as possible before combustion. So we needed to maximize the heat exchange rate. But at the same time, the amount of pressure drop of the heat exchanger steals from the downstream engine and it takes away from the horsepower of the engine too. So it was really vital to maintain a low airside pressure drop at the same time as getting the most cooling power out of the air. So we approached this in an interesting way. We actually were able to split the airflow into two streams. where we were able to put 2 parallel heat exchangers into each stream, which helped us slow down the fluid and really squeeze out the most heat exchange we could out of the air. By being able to dig in deep and optimize the geometry in our device, we're able to save a lot of weight. We're able to drop an alternative solution would have been about 16 kilos to get the same heat transfer. We're able to drop that down to about 2.8 kilos. And a big advantage was we're able to shorten the airflow length of the part by about 50%. And this helped the component be reconfigured and the system itself get reconfigured. Air ducts and things like that were able to be shortened too. All of that performance gain, and we were still able to minimize the airside pressure drop, dropping it by 12% below the target. And by having quite friendly fluid pathways for the coolant, we were able to drop that by 65%, the pressure drop in the coolant as well. And this is by just really nicely controlling the flow of the coolant through the device. Now, our next and final case study is an argon gas cooler that we had to create on behalf of AMCM. And so this component went into an AMCM 3D printer as well. They needed it to be monolithic. They needed to cool down the argon to below 25 Celsius. And what was most important for them was being able to minimize the pressure drop and the flow resistance on that argon gas. This really helped to ensure stable operation in the device as well. So there's a low argon limit that was imposed, and the approach we took was to really focus in on minimizing the pressure drop while still meeting the heat exchange target. We did so by creating a counterflow solution where we integrated the core and the manifold together. And we did some really interesting stuff with design for additive manufacturing. It's not shown here, but there's some lovely veins as the argon gas enters the gas duct. We've put in a lot of structure and veins to help support and strengthen the air side or the argon side manifold, but also help really distribute well the flow to all areas of the core. Now, we were able to by putting so much effort into optimizing, we were able to actually reduce the footprint of the device, so the overall volume, by 93%. And there's a bit of a comparison image up there on the left, which just shows how significantly smaller our component is. We were able to do this while still meeting the heat exchange target, and most importantly, driving down the pressure drop throughout the core and throughout the manifolds as well. So this is all I've got for the case studies. I'd love to hear questions and answers.